Swayam Prabha. Digital India. Educated India.
Welcome to this lecture on advanced manufacturing processes under module 2. I am Dr. Apurva Kumar Sharma from the Department of Mechanical and Industrial Engineering from IIT Roorkee. Dear students, in this session we will study about the metal casting process and its importance, the basic phenomena involved in metal casting process, the gating and risering systems. Casting is one of the earliest metal shaping methods known to human beings. Generally, casting means pouring molten metal into a refractory mold with a cavity of the shape to be made and allowing them to solidify. On solidified, the object is taken out from the mold either by breaking or by taking the mold apart. The solidified object is called casting. Thus, in a single step, simple or complex shapes can be made from any material that can be melted. It is almost impossible to design a part which cannot be cast. Let us see a formal definition of casting. I quote, "A casting is a shape obtained by pouring liquid material into a mold or cavity and allowing it to freeze and thus to take the form of the mold." Unquote. Let us peep into a little historical background of this process. Casting was probably discovered around 3500 before Christ in Mesopotamia. These molds were essentially of single piece. Bronze Age, which is estimated at 2000 BC, brought more refinement into the casting process. Molds were made of baked clay and the Shire Purdue or lost wax process was used for making ornaments, etc. The technology was greatly improved by the Chinese from around the year 1500 BC. The Indus Valley civilization has the evidence of cast product too. Here is a photograph of a cast mold. Now, let us see the casting problem. The casting problem can be basically divided into two areas: the design and production of the mold, and number 2, the melting, refining, pouring of the liquid metal. In design and production of the mold, the following are addressed: mechanism and rate of solidification, heat transfer during solidification, the flow of liquid metal, stresses in the metal in solidus temperature range, stresses in the elastic range, mold materials and production methods. The mechanism and rate of material solidification involves the crystallization pattern and estimation of shrinkage in volume during solidification for calculation of the risers to be placed and proportioned properly. These factors vary considerably depending upon the chemical composition of the material and thermal gradients in the mold. Thus, in this process, engineering analysis tools can help significantly. The melting, refining, pouring of the liquid material aspect is generally studied through number 1, gases in materials, number 2, control of common elements, and number 3, selection and control of melting furnaces. Now, let us look into the solidification process. The time taken for solidification of casting is relatively a very brief period in the entire production history. During this short time, the original crystal structure of the casting is formed, which is considered the backbone of the casting, on which many other properties depend. In this interval, major flaws such as shrinkage, porosity, hot tears and seams can be prevented depending upon the care with which the solidification has been planned. Let us now discuss crystal nucleation process. There are two types of nucleation. Number 1, homogeneous nucleation. Homogeneous nucleation is the formation of a new phase without the help of special nucleation sites. Number 2, heterogeneous nucleation. In heterogeneous nucleation process, solidification process in which the solid phase crystallizes on foreign nuclei. The temperature at which the homogeneous nucleation takes place is always below the equilibrium freezing point, because it is necessary to overcome the surface tension forces which slow down nucleus growth. The energy required to produce a nucleus of solid is the difference in free energy per unit of the volume between the liquid and the solid phases. This energy, also called the bulk free energy change, is designated as delta F(V), which is expressed in calories per square centimeter for a given temperature of supercooling. At all temperatures below the freezing point, delta F(V) is negative, that is, the solid phase is then more stable and therefore has a lower free energy than the liquid phase. The bulk free energy change associated with the formation of a spherical particle of radius r is given by 4/3 into pi r cube into delta F(V). The energy required to create the new surface is a function of the surface tension sigma, which is expressed in ergs per centimeter square, and the corresponding energy is expressed as 4 into pi r square into sigma. The net free energy change del F(V), del F is then expressed as del F equal to 4 pi r square into sigma plus 4/3 pi r cube into delta F(V). Once the critical radius r star is exceeded, further growth results in a decrease of free energy and can proceed spontaneously at the temperature of supercooling. This is shown in figure 1. Here, this is the critical radius r star. If a particle has a radius smaller than r star, it will redissolve because this decrease in size reduces the free energy. The size of the critical radius may be found by differentiating the above relationship with respect to r and setting the result equal to 0, which then yields r star to be equal to minus 2 sigma by delta F(V). The r star relation indicates that for r star to become very small, del F(V) must become very large in a negative sense. That is, severe supercooling is needed for homogeneous nucleation. Also, the term sigma does not change greatly with temperature. On the other hand, delta F(V) increases with supercooling and therefore causes a very small nucleus to be stable. Let us come into heterogeneous nucleation process. Most actual castings crystallize by heterogeneous nucleation process. The reason being, if the new phase can find a foreign particle to grow upon, it can adopt the relatively large radius of the particle as its own. It means only a slight degree of supercooling is needed in comparison with that needed for homogeneous nucleation. Quantitatively, the relation depends upon the degree to which the new phase wets the foreign particle. If there is no attraction between the atoms of the foreign particle and those of the participating phase, then nucleation is not helped. The wall of a mold usually provides many heterogeneous nucleation sites. That is how the solidification process begins. Let us see an example of solidification of a pure metal. Those nuclei which happen to be formed with the preferred growth direction perpendicular to the interface grow more rapidly than the crystals of other orientations. This leads to the growth of columnar grains advancing towards the center of the ingot. The final structure therefore consists of a thin layer of randomly oriented grains at the mold surface and columnar grains extending to the center line. In this situation, there are no randomly oriented grains at the center of the ingot. Solidification of axial castings. The solidification of alloys differs in three principal ways from that of pure metals. Number 1, usually the freezing of alloys occurs over a temperature range. Number 2, the composition of the solid which separate first is different from that of the liquid. And number 3, there may be more than one solid phase crystallizing from the liquid. Now, let us see a gating system. The assembly of channels which facilitate the molten metal to enter into the mold cavity is called the gating system. This is shown in the figure 2. Alternatively, the gating system refers to all passageways through which molten metal passes to enter into the mold cavity. This is a typical gating system in which this is the pouring system. The molten metal comes through the sprue which is constructionally tapered in shape. Then the liquid metal is distributed through this gating system into the various cavities. What are the goals of gating system then? This is to minimize turbulence to avoid trapping gases into the mold. Then to get through enough metal into the mold cavity before the metal starts to solidify. Then another goal is to avoid shrinkage. To establish the best possible temperature gradient in the solidifying casting, so that the shrinkage, if occurs, must be in the getting system, not in the required cast product. Thereby, it helps in retaining the appropriate or desired tolerances. It also incorporates a system for trapping the non-metallic inclusions. The major design principles of getting system are as follows. Turbulence can be avoided by incorporating small changes in the design of getting system. The sharp changes in the flow should be avoided to smooth changes. The getting system must be designed in such a way that the system always runs full with the liquid metal. In getting system design, sharp corners should be avoided. Any changes in direction or cross sectional area should make use of rounded corners. To avoid the aspiration, the tapered sprues are designed in the getting systems. A sprue tapered to a smaller size at its bottom will create a soak, which will help keep the sprue full of molten material. Types of getting systems. The getting systems are of two types: pressurized getting system and unpressurized getting system. In pressurized getting system, the total cross sectional area decreases towards the mold cavity. Back pressure is maintained by the restrictions in the metal flow. Flow of liquid is almost equal from all gauges. Back pressure helps in reducing the aspiration, as sprue always runs full. Because of the restrictions, the metal flows at high velocity, leading to more turbulence and chances of mold erosion. Unpressurized getting system, on the other hand, the total cross sectional area increases towards the mold cavity. Restrictions only at the bottom of the sprue is given. Flow of liquid is different from all gauges. Aspiration in the gating system, as the system never runs full, there is less chance of turbulence. Now, let us consider the risering system. Riser is a sprue of extra metal which flows from riser to mold cavity to compensate for shrinkage, which takes place in the casting when it starts solidifying. Without a riser, heavier parts of the casting will have shrinkage defects either on the surface or internally. Risers are known by different names as metal reservoir, feeders or headers. Shrinkage in a mold from the time of pouring to final casting occurs in 3 stages. Number 1, during the liquid state. Number 2, during the transformation from liquid to solid, and the number 3, during the solid state. The first type of shrinkage is being compensated by the feeders or the gating system. For the second type of shrinkage, risers are required. Risers are normally placed at that portion of the casting which is last to freeze. A riser must stay in liquid state at least as long as the casting and must be able to feed the casting during this time. Now, let us see the functions of a riser. It provides extra metal to compensate for the volumetric shrinkage. Then risers allow mold gases to escape. They provide extra metal pressure on the solidifying mold to reproduce mold details more exact. Now, what are the design requirements of risers? First is the riser size. For a sound casting, riser must be the last to freeze. The ratio of volume to surface area of the riser must be greater than that of the casting. However, when this condition does not meet, the metal in the riser can be kept in liquid state by heating it externally or using exothermic materials in it. The way the riser is connected to the casting is very important. The connection called neck should solidify first, so that the shrinkage cavity is located in the riser itself. The removal of the riser should be made simpler, making the neck smaller. But in too small neck, the neck might get solidified earlier than the casting, hence defeating the whole purpose. A normal practice is to provide a thin ceramic or core material for the neck to reduce the cross sectional area. These are called Washburn cores. Let us see few basic terminologies associated with casting technology. This will be useful throughout this module, because we will be dealing with most of the casting techniques at various point of time. Some of these are illustrated through sketches in figure 2 and 3 later on. One very important terminology associated with casting is core. This is made by a special process which enables create a hole or internal passage within a casting, which is very important as far as the casting technology is concerned. Then chills. These are metallic pieces which are kept at those bulk sections which need to be cooled faster. They eventually help to provide uniform solidification. In other words, or in thermodynamics terminology, heat transfer terminology rather, we can call these as nothing but some kind of heat sinks, like we use fins in some cases. So, these metallic materials provide larger area which are in contact with the heated object or in the vicinity to the heated object, so that the rate of heat transfer can be faster. As we know, rate of heat transfer is proportional to the area of heat transfer. Therefore, this is nothing but a technique to enhance the heat transfer area. So, what is the advantage of this? The advantage is, as the rate of heat transfer becomes faster, then the solidification can be homogeneous. Otherwise, in some cases where the section is thicker, then molten material is, the quantity of molten material is higher, and therefore, it may take more time to get solidified, or rather to reject the heat from the molten metal and thereby getting solidified. However, with the use of chills, this can be avoided, or the situation can be enhanced in the form of providing higher area for heat transfer, and thereby the rate of cooling becomes faster, and therefore, consequently the entire body of the casting can get cooled at more uniform rate with that of the thin sections, which are in any way getting cooler fast. Another important term quite often used is chaplets. These are provided in case of weak cores or weak sections, as we have just now discussed. The cores are nothing but some holes or the passes provided. So, therefore, by providing passes, in some cases it may so happen that the section becomes very weak, which may not be eventually possible or to withstand the load of molten metal. Therefore, these chaplets are used to strengthen these weak sections. Its composition is almost same as that of the final casting, so that the diffusion or other problems are minimized. Initially, a chaplet provides support to the core in the casting, and eventually it melts and forms a part of casting. That is why the similar composition is preferred, so that the cast product do not lose the property, or the properties of the final product do not get deviated from what is designed. Another important one is pattern, which we will be using almost in the every session that will be discussed in this module, that is pattern. It is the replica of the required cavity or shape. It resembles the required casting with allowances in it. it is made of wood, metal, wax or plastics as the situation permits, or as the situation could be. Say for example, wax if we use, they are lost because of the coming in contact with the very high temperature molten material. On the other hand, if metallic patterns are used, they can be reused for several cycles. Then another important characteristic with this pattern is there should be adequate allowances provided on the pattern dimension, like some allowances may be required on account of shrinkage. As we know, solid materials shrinks as it cools. Therefore, the molten material as it gets solidified, its volume gets shrunk. Therefore, if we prepare a pattern with exact dimensions of what is required, say 50 mm, if we produce 50 mm of pattern, then at the end of the day, upon solidification, we may end up with a pattern having dimension of 49 mm or 48 mm as the case may be, depending on the expansion coefficient of the material. Therefore, this needs to be taken care of. The data regarding which are readily available in handbooks, that which material will undergo how much of percentage of shrinkage, and accordingly the pattern can be made oversized to account for this shrinkage. Another important aspect in this pattern is the final finishing. Some of the patterns may need post processing. Say for example, post processing due to some achieving some pre-required or prerequisite surface finish. For these to achieve, say from 100 micrometer to Ra equal to 50 micrometer, what I need is in between some reworking or some material I have to remove from the original cast, or this is, we can say this is raw casting. This process may be say grinding or some other finishing process. Now, from where this additional material will be sacrificed? This indicates that we may have to allow some additional material in the raw casting itself. That means, the pattern has to be made little oversized, so that it produces a little bigger casting as required, and this bigger or the additional material will be removed like this as part of the finishing process as we have discussed here, which will ultimately give us the required dimension. This is required dimension. Another important term very closely associated with molding technology or casting technology is the mold box. It is the flask which contains the mold material in it. It can be single box or two boxes or multiple ones. In case of double box, the top is called a scope and the bottom box is called drag. Then molding material. In most of the cases, sand is the desired molding material, since it has high refractory property as well as they are cheap. Sand is mixed with other ingredients as desired, like to make them more flowable, etc., or in some cases to make them more binding, binders are used, and so on. Then sand molding ingredients. So, these are sand, clay and water. These are some of the ingredients. In some cases, some other materials as binder are also used, like clay content, etc., can be used to give the binding properties. Then the core. What is a core? It is a hard sand shape which is placed in the mold to give the desired holes or internal cavities. What is a core print? This is another important term. It is the region added to the core or pattern, usually at its ends, which helps it to sit in the cavity in the proper region. Then core seat. The corresponding section in mold where the core print gets located is called as the core seat. Another important term is ladle. Ladle is a device having a crucible with handles as its ends. It is used to carry the molten metal from the furnace to the molds. There are different types of ladles to suit different requirements. So, this is a generalized picture as displayed in the screen. So, this figure describes almost all the important terminologies associated with the casting process. Like this is the core as we were talking about, and this is the core print. This core is the hole or the passage for the molten material to pass from, say this is the pouring cup, this is where the molten material will be poured and the material will settle here, then it will flow through this and this needs to be flown to this part and this part. These are the chills that we were talking about, the metallic portions, those are provided for enhancing the heat transfer inside the core, inside the casting. So, here we can notice as we have already indicated. So, this is the, I think this is as the figure shows, this is the largest section of this particular casting. Therefore, it ideally contains more quantity of molten material and therefore, it will take longer time to get solidified, because heat content will be high and this contained heat to be transferred out, it will take more time, provided the area around it or area through which the heat will get transferred remains same. To improve upon this situation, because this here this casting has got different sections. like some sections are relatively smaller than this section. Therefore, there is a possibility that this thinner sections will get solidified earlier to that of larger sections. To eliminate this inhomogeneity in solidification, these shields are provided, as can be seen here. These are metallic plates which acts as the heat sink and helps in providing better heat transfer rate in these large sections, so that non-uniformity in heat transfer, rate of heat transfer at different sections of the casting gets reduced. And as far as the box is concerned, I was talking about just few minutes back. Here in this particular figure, there are two boxes provided. One is called cope, the top box, and this is the parting line, and this is the drag, lower portion, lower half of this box. This is called drag. Next is the pouring cup or pouring basin. This we have seen in the figure also just now. It is the initial region in the gating system which first receives the molten metal from the ladle and allows it to move through. Then the runner, it is the horizontal passage which connects sprue with the gauge. It passes molten metal to the subsequent sections. Then gauge, these are passages which connect the runner to the in gauge. In gauge, these are the last openings in the gating system which connect gauge to the cavity. In some designs, gauge and in gauge are both same. So, this is a typical gating system we were talking about. So, this is the sprue and this is where the molding cup we can this pouring cup we can say, and from the ladle the liquid molten material will be poured here. This will facilitate the molten material to flow through, and this is the gate through which the material will be delivered to the cavity where the casting is to be produced, and these are the in gates. This number of branches are being created, so that the distribution of the molten material will be at a uniform rate, and of course, this will help in maintaining uniform temperature as far as possible while delivering. And this is the riser which provides additional molten material, so that during solidification, if the molten material shrinks, which usually happens, liquid occupies more volume in most of the cases, and while solidification the volume gets shrunk, then to fill the remaining portion, this riser provides additional molten material which it keeps as the reserved one, or uses this reserved molten material will be used, so that no void or volume is left unfilled inside the casting because of the solidification. Then another terminology very important as far as the casting is concerned is the draft. It is the taper provided on the pattern which allows easy withdrawal of the casting from the mold. This we can see in the previous figure as well, as a taper. Now, let us summarize what we have discussed in this particular session. We have discussed the basic features and terminologies in casting process, getting risering systems and their design aspects, the basics in solidification or the casting formation. We hope this session was informative and interesting. Thank you.